Good evening. Welcome to what is now the sixth of these quarterly Frontiers of Cosmology lectures that have been organized by the UCR Physics and Astronomy Department and its new Center for Experimental Cosmology and Instrumentation. This initiative is being supported by a new center, which we call CESI. This is There we go. This is an initiative being led by one of UC Riverside's two Nobel Laureate faculty members, Professor Barish, who we'll hear from later tonight. The goal of this center is to create transformative new enabling detector technologies to see the universe in different ways across the electromagnetic spectrum with gravitational waves and through particle messengers. The idea of CESI is to unify many of the department's existing strengths in astronomy, cosmological theory, material science and engineering, and to bring them all together to develop frontier detector technology for the next generation of cosmology experiments. There is a vision to build a new center which will feature a world-class experimental research center right here in the Inland Empire of California. And so we're very much in a fundraising phase right now to actually launch this new center. If you are interested in supporting the center tonight, any gift amount is greatly appreciated. It goes to directly supporting students in the research of this new center. And we would like to especially thank many of our friends and supporters who have already been supporting CESI. So I would like to remind everyone that at the end of Professor Marston's talk tonight, there will be a question and answer session. We have two microphones that will be set up in the front of the room. And so if you'd like to ask a question, we ask that you please just form a line in either of the two aisles, and we'll have a few minutes for questions. So with that, I would like to introduce UCR Provost Elizabeth Watkins.
Thank you, and thank you all for being here. Look at this crowd. This is a full house. I am so excited to see all of you here. I see, obviously, we have our UCR students, we have UCR faculty, but I also know that we have science teachers from the area, we have high school students, we have middle school students, and I'm just thrilled that you're all here for this lecture. I also understand that we have attendees from the 42nd Pacific Coast Gravity Meeting. This annual conference of the American Physical Society's Division of Gravitational Physics is being hosted by UC Riverside for the first time in its 42-year history, so welcome to all of you. And I also want to extend a very special welcome, of course, to our speaker tonight, our keynote speaker, Professor Brad Marston. Professor Marston got here from Rhode Island, which is my home state, fought all the snow that they've had on the East Coast to make it out here. And so we're so grateful for the time that you're taking, for the opportunity that we will have to learn from you as we explore the frontiers of cosmology together. So we're here tonight, this evening, to peer into the furthest reaches of the universe. But we're also here to celebrate this new center of innovation right here in the Inland Empire. As you heard earlier, this event is being hosted by UCR's Center for Experimental Cosmology and Instrumentation, also known as CC. Launched just a couple of years ago, in 2024, CC was established to answer the most fundamental, timeless questions about where we came from and what our universe is made of. And we are very proud that the center is being led by Professor Barish. As many of you know, Professor Barish's work on the LIGO project earned him the Nobel Prize in Physics, and his leadership here at UCR is a vital asset as we expand our research footprint in experimental cosmology. Now, under Dr. Barish's leadership, CC is not only theorizing about the cosmos, it's also developing the tools to observe it. Our researchers are exploring the nature of dark matter and dark energy, and observing events such as colliding black holes and merging neutron stars using technologies that were beyond our reach barely a generation ago. But CC's mission extends beyond just the observational. The I in CC stands for instrumentation. And it's the technology being developed in our labs that has such extraordinary translational power. The same sensors and tools we use to detect gravitational waves from billions of light years away have the potential to lead to new applications in industry, communications, and medical imaging. And we saw this potential last year when Congressman Mark Takano met with the center researchers to discuss how the technologies being developed at CC support not only fundamental research, but also the broader economic infrastructure of our region. And perhaps most importantly for us here at UCR, CC is a training ground. The undergraduates, the graduate students, and the postdoctoral fellows working in these labs are gaining high-level technical skills required for leadership roles in both academia and the private sector. Now, to our neighbors and community members here tonight, remember that CC is your center, too. We want you to feel a sense of ownership over the incredible scientific developments happening right here in your neighborhood. Tonight, as we listen to Professor Marston, I invite you to think about the scale of what we are discussing. We're part of a vast, mysterious universe, but we're also part of a vibrant, growing community that's determined to understand it. And it's your support that will allow us at UCR to continue to keep pushing these boundaries. So, thank you all for joining us this evening, and I'm now going to turn things over to my colleague, Dean Peter Atkinson, Dean of the College of Natural and Agricultural Sciences. Dean Atkinson.
Thank you, Provost Watkins. So a warm welcome to everyone, and yet again, another full house for a Cosmology Science Series lecture. This is phenomenal support and illustrates the excitement and the curiosity for this particular area in our county, in our region. So I'm going to be introducing Barry Barish. Barry is a professor of physics here, and he has won through his career a host of preeminent awards, and the most famous would be the Nobel Prize in Physics a few years ago for the discovery of gravitational waves. But the most recent award is from the American Philosophical Society in 2025, and this society is in fact the oldest learned society in the United States, being founded by Benjamin Franklin in 1743 in the then colony of Pennsylvania. And its mission was to promote useful knowledge. And the array of societies that Professor Barish belongs to, both in the United States and throughout the world, is immense. And we are honored that he has chosen to be a professor here in our Department of Physics and Astronomy at Riverside and is leading this charge. One of the best things about my job is events like this, when I see the initiative of faculty, students, staff to do new things, to come up with challenges and to meet those challenges, and to take the departments, maybe one department, maybe groups of departments, maybe departments across colleges, in a new and exciting direction, and to start building and to get people involved. And you think about the students out there, years, elementary, middle to high, who may not be here, are not here, and yet the future awaits them here because of the very initiative that Professor Barish and his colleagues are pioneering. And so as an individual scientist, as Dean of the College, and on behalf of the college, a sincere thank you, Barry, for everything that you have brought to our campus, to our college and department. And what further proof does anyone need than the outstanding interest in all of these series, and now again tonight. So Barry, thank you so very much.
Okay, you've heard a bunch of speeches. My task is to introduce the speaker. So I'm delighted to introduce Brad Marston tonight. He's a professor of physics at Brown University. He got his first degrees, a BS from Caltech down the street in 1984. Then he got a PhD in Princeton in 1989. And since that time, he's had a long and successful career. But the kind of way he approaches science, I think you'll get a good sense of it in the lecture tonight. But before we get to the lecture, I want to note something else. And that is, as of January 1st of this year, I think January 1st, he became president of the American Physical Society. That's our Society for Physics. And I served as president, so I know what the job is, or what it was, in 2011, 15 years ago. So lots of change has changed since that time, but it is basically our society. And I know a lot about kind of the important things that society does and the challenges that it entails. Brad was elected by 50,000 members of, 50,000 members. They didn't all vote for you necessarily, but there are 50,000 members in the APS. It's a worldwide organization, so it's mostly American, but it really has, because American trained scientists are everywhere in the world or want to be connected to American science. And members are in academia, like us here, in the national laboratories, in industry, and as I said, around the world. The APS is also the distributor of our science. They publish 19 of our most respected scientific journals, and they sponsor some of the most important physics conferences that we have, where we come together and present new results. But beyond that, the APS officers have a special role of representing physics and science more generally to our government and to the public. I point out that there are essentially no scientists that hold positions in the present administration. So the APS president this year has a special challenge and responsibility, and Brad and I have talked about this, to represent physics and science in Washington, D.C. And we owe him a lot of support in his task to do that. As for tonight's talk, the best way I can describe Brad's research career is that he's mastered some fundamental concepts in physics, and then he's used them to apply to understanding physics in very different areas of the physical world where the same principles apply. I imagine, I just saw the title, I don't know anything more. I imagine that today's lecture will continue this general theme. In this case, the physics is that of waves, something we all study when we study physics. And from the title, I assume that Brad will discuss waves in very different phenomena. So tonight's title is Waves Are Everywhere: How Oscillations Shape Technology, Earth, and the Universe. Brad Marston.
Very much, Barry, for that kind introduction. Thank you, Dean Atkinson, Provost Watkins, Professor Richardson. Okay, yes. So I want to tell you about how waves are everywhere and how oscillations shape technology, the Earth, and the universe. I'm really glad to be here. Yesterday, day before, it was looking kind of unlikely. This is, microphone's on here. volume can be turned up. Yeah, it's switched on there.
So we have to use the back.
All right. Yes. Oh, good. My trip yesterday here began by a sled ride because it had snowed 3 feet in 12 hours in Providence, Rhode Island, breaking all records. And in fact, Provost Watkins was just telling me that she was in Rhode Island during the previous record-breaking blizzard, the blizzard of '78, which paralyzed the state. We were a little bit better prepared this time. The forecasts have improved. And there's a lot of really good wave physics in this. So I haven't included that in the talk tonight, but if there's some questions about the wave physics of northeaster storms, I'd be happy to chat about that. All right. So this is a kind of a whimsical diagram from a British physicist named Lighthill that summarizes just some of the many types of waves that we encounter in nature. We have sound waves that you're hearing right now, light waves you're seeing, tides. We have Rossby waves; those are related to those big storms. We have waves in magnetized plasmas. We're going to talk about that a little bit later tonight. Waves in rotating systems. We'll talk about that also. But there are also even more exotic waves, waves that, for example, Professor Barish has been investigating. So just from this, we can see that there's a lot of variety out there, but there's some commonalities, and I want to explore both those varieties and commonalities with you tonight. Now, this is a picture of a young William Thomson, a famous physicist who later became known as Lord Kelvin. And he made seminal contributions to our understanding of waves, along with many other things. He wrote a paper in 1879 entitled On the Gravitational Oscillations of Rotating Water. He was concerned about waves in the English Channel and had the observation that they intended to be stronger along the French side of the channel than along the English side. So he was accounting for gravity and also the rotation of the Earth, the Coriolis force. And what he discovered back in 1879 is something that quantum physicists only rediscovered in the 1980s. There's a close connection between these two things that I want to tell you a little bit about. So let's begin with an experiment. What we're doing here is we're looking down on a wave tank, and it's filled with some water and another fluid. And on one side, there's a source of waves, basically just making the water go up and down. And you can see the oscillations in the water height with this setup. It's using polarized light. Over on the right is exactly the same system. It's the same wave tank, but now let's put it into rotation. So it's going to be rotating, and the camera is going to be rotating with it. So we're not going to see the dish rotate, but we're rotating with it. And with that same source of waves, we see now the waves are confined to the edge of the tank. And these are what we now call coastal Kelvin waves. These are the waves that Kelvin, Lord Kelvin, William Thomson sought to explain and did so in this beautiful and very short paper back in 1879. And it turns out that those waves have an origin in the mathematics of topology. So what is topology? It's basically the qualitative shape of things. So if we imagine a coffee mug that was made of Play-Doh, and it has a little hole here in the handle, we could deform this Play-Doh continuously into a donut without tearing that Play-Doh. donut has one hole in it, and so does the coffee mug. So this is an example of something that is topologically equivalent. That we would say that the donut or the bagel is the same thing topologically as that coffee mug. A Mobius strip is another example. We take a strip of paper and we give it a twist and tape it back together, and we have a surface that doesn't have an inside or an outside. If we start on the inside, what seems to be the inside, we move to the outside, and as we go around, then eventually we'll be back on the inside again. If we wanted to have a definite inside or outside, we'd have to cut that strip of paper and tape it back together without the twist in it. So as long as we don't do anything violent, like cutting or tearing, then the topology of these shapes remains the same. There's another theorem called, or example called the hedgehog theorem or the hairy ball theorem. If you imagine you had a ball with hairs everywhere on it, and you wanted to comb them flat and make it nice and neat, you'd find out that that was impossible. There'd always be a cowlick or a bald spot on this sphere. But if the hairs were on that donut, you'd be allowed to do that. You could lay them all flat. So this theorem is sometimes called the hedgehog theorem. In Europe, it's called the hedgehog theorem because they have hedgehogs in Europe. And this is a pretty good approximation to a sphere that has hairs all the way around it. And you can see that they're not laying flat. So Richard Feynman, in his lectures on waves and turbulence, wrote, "The next great era of awakening of human intellect may well produce a method of understanding the qualitative content of equations. Today we cannot. Today we cannot see that the water flow structure between two rotating cylinders, this is called rotating Couette flow, contains this nice structure, sort of a barber pole structure. Today we cannot see whether Schrodinger's equation in quantum mechanics contains frogs, musical composers, or morality, or whether it does not." So this advance, this realization that topology plays a role in physics is a small step in the direction that Feynman was talking about, a qualitative understanding of complicated equations that allows us to bypass having to solve them directly. So topology can turn some complicated problems into simple ones. And although Kelvin didn't realize it at the time when he did a direct solution of his equations, topology was actually the explanation for that wave working around the coast. Now, a number of years ago, we had a search for a new faculty member in solid state physics in my department, and I was on the search committee. And when they came into my department, into my office, I handed them this book, Geophysical Fluid Dynamics, and they wondered, why am I handing this book to them? Because this is a completely different field of science. But I had a page marked to this drawing, which for the experts in this audience, this is the dispersion relation of Kelvin waves, the coastal Kelvin waves. And I didn't have to say anything. The condensed matter physicists, the solid state physicists, as soon as they saw this diagram, they understood completely what Kelvin had been doing back in 1879, because they had been seeing diagrams like this in many talks about solid state physics. They've been seeing this in the field of topological insulators, a seemingly completely different area of physics, but actually intimately connected with the fluid dynamics from the 19th century. And this connection had been missed by generations of physicists because physics has been siloed into different fields. Geophysicists don't go to condensed matter or solid state seminars and vice versa. So there was the opportunity, a missed opportunity to understand this connection well before it was finally made. So these kinds of waves don't exist just on the edges of water, on coastal boundaries. They also exist along the equator of the Earth. So let's imagine dropping a rock into a pond, and we see the waves shooting out from that center point. So that's due to the role of gravity, which is causing the water to oscillate up and down. If we do this on a sphere in a simulation, the waves go all the way around the planet and pass through each other and then come back. And they'll just go back and forth, back and forth. If we look at this on a latitude and longitude coordinate system, we can see these waves going back and forth. But now, if we put this planet into rotation, something very different happens. The waves are now confined to the equator of the planet. So there's something very special about the equator there. And they really come in two types. This is now known as a equatorial Kelvin wave, and there's a second wave called a Yanai wave, but they're both confined to the equatorial region of the planet. Now, Mother Earth did an experiment a little bit like what I showed in that simulation. A few years ago, there was a huge underwater eruption in the Pacific, the Honga Tonga eruption. And if you look in the center of this movie, what you're going to see is a pressure wave that is going outward from the explosion site at the speed of sound in this satellite view. And there's the wave shooting out. So this wave wasn't deflected by the rotation of the Earth because it's a different type of wave. It's a pressure wave, but it did go around the Earth back and forth several times before it faded away. In the case of the Earth, the Kelvin wave is a very important wave in the climate system because it's part of the El Nino climate oscillation, the largest climate oscillation that occurs on a time scale of a few years. And this NASA video shows the height of the ocean as measured by a satellite that's using microwaves, basically radar, reflected off the surface. And you can see this wave propagating from the west to the east along the equator of the Earth. It's colored red because, so red represents here a little bit higher surface, water surface than normal, and that is associated with warmer water. Water, when it is warmer, expands, and when this warm pool of water is off the coast of South America, we're in the El Nino phase of this oscillation, and that has worldwide climate impacts, and in particular increases the chance of intense rain in Southern California. Right now, we're in the opposite phase, La Nina phase, and that's the phase where New England tends to get these heavy snowstorms. So that may be partly behind what happened a few days ago. We're just now moving out of that La Nina phase back into an El Nino phase. Now, I want to turn to some other types of waves, and I want to sing the praise of this physicist, James Clerk Maxwell, who is not as well known as some other names like Newton and Einstein, but I think deserves to be as well known as those two physicists. So Maxwell is famous for understanding the relationship between electricity and magnetism, and from that predicting the existence of electromagnetic waves. And I would argue that although he made his discovery in the middle of the 19th century, it really is, in some sense, a discovery that relies on physics from the 20th century. Although it wasn't understood quite at the time, his equations have the full theory of relativity, Einstein's theory of relativity built into them, and Einstein only discovered that back in 1905. So some 50 years later, and also contains the seeds of quantum physics. There's another physicist a little bit later in time, Oliver Heaviside, who took Maxwell's equations and put them into the modern form that we're used to. And he's important, as we'll see, for another reason in our understanding of communications. So here's a picture of a statue of Maxwell in Edinburgh, Scotland that I took in January when I was there for a meeting. And here are his equations put in the form that Heaviside put them in too. And one of the stunning predictions of these equations was the electromagnetic radiation, light, radio waves, X-rays. These were all manifestations of the same phenomena, oscillating electric and magnetic fields, with the difference being the frequency or the wavelength of those waves. So here it's visible light in the middle at a frequency of about 10 to the 14 hertz. And we have the radio waves down here, and we have X-rays and gamma rays in the very high frequency range. And so this, and the corresponding wavelengths of these waves corresponds to the size of buildings, human beings, going down to bacteria, and then to the atomic scale. So another scientist, Hendrik Lorentz, realized that Maxwell's equations were incompatible with the laws that Newton and Galileo had written down. And he realized that in order for Maxwell's equations to hold, it meant that objects would have to do some very funny things. They would have to contract in size, for instance, when they're moving. We call that the Lorentz contraction. But he didn't really understand the full scope of this, what this really meant in terms of more basic physics. And that was, that task fell to this man, Albert Einstein, who realized that space and time were connected together intimately, and that an understanding of that, plus the fact that the speed of light is the same regardless of what frame you're in, how fast you're moving, that led to the kinds of physics that Maxwell's equations respected. So what practical impact did this work have? I find it amazing to realize that the first transatlantic cable for telegraph was laid down around 1850. So in 1850, there was some beginning, you can imagine, of the internet with this fantastic increase in communication speed. Previously, it would take months for a message to go from, say, the United States to Europe. And now it could travel much faster. So this is the diagram of the early cables. So you can see they're trying to span the ocean in the shortest possible distance. And the reason for that is that the signal strength got very weak, and the longer you had to go, the weaker it got. But also, the signals transmitted at a very slow rate. So even though it was a huge increase over boats, they could transmit only about 1 or 2 words per minute. So very slow by modern standards. And it wasn't understood why it was so slow. And furthermore, there was the idea that, well, maybe the signals are so slow because we're not using enough voltage. Let's just crank up the voltage and really send a powerful pulse down that cable. Well, they tried doing that. William Thomson, Lord Kelvin, told them that was a bad idea and that you should just build a very sensitive detector. They tried it anyway, and they burned out the cable and it shorted it out, and they had to lay down another cable. But, and of course, nowadays, we have fiber optics that can transmit messages at basically the speed of light, millions of messages, and these are used to transmit huge amounts of information. But this episode with the slow communication illustrates the importance of physics understanding for technology, because Heaviside had worked out the theory of transmission in cables several decades after that first transatlantic cable, and realized that the cable had a lot of capacitance but not much inductance, and that it needed some inductance to speed up the transmission of the signals. So Heaviside developed the modern theory of transmission of electromagnetic waves, and that once that was understood, it became possible to greatly speed up telegraph signals over large distances. Now, another manifestation of this electromagnetic radiation is the glow left over from the Big Bang. This is a representation of the expansion of the universe from the Big Bang to the present period, so a vast 13.77 billion years. As the universe cooled from this incredibly hot initial state, the atoms that had been ionized, the electrons had been removed from the positively charged nuclei. These recombined together, and when they combined back together, then the light that was trapped by scattering off of all of these electrons and positively charged protons could then be free to move through space unencumbered by the interaction with this hot plasma. And what we see today in the microwave background radiation that is the subject of investigation here at CC, for instance, is this remnant from this radiation that escaped from being blocked by this hot early period in the universe. And so we see these fluctuations in the brightness of the sky at microwave wavelengths. It's greatly, the fluctuations are very small. It's greatly exaggerated in this view so that we can see them. And these fluctuations eventually grew into the structure of the universe. And we'll see a video at the end of the talk of the large-scale structure of the universe. So I want you to keep that in mind, that the light waves from this initial period way back in the beginning is conveying information about how the structure of the universe would subsequently evolve. And it evolved through pressure waves, density waves, from the initial fluctuations after the Big Bang. Now, there's another system that has some similar physics to it, and that's planet Earth. When we look at planet Earth from space in infrared channels, so wavelengths a little bit longer than visible light, corresponding to the wavelengths that water vapor absorb and emit infrared radiation, then we see this beautiful picture. This is from another NASA satellite. We can see, first of all, that there's a difference between the equatorial regions where these buildup of thunderstorms during the daytime, and then they die back at night. And then these waves at high latitudes, those are the Rossby waves. So those are the waves that basically govern the propagation of storm systems. But you notice something else. Like the usual pictures of Earth that we see in the visible light, you can't recognize any continents. You can't see anything below about 5 kilometers because at the lower 5 kilometers of the atmosphere, there's so much water vapor that the infrared photons can't, if they leave the surface from the warm surface and they try to go out into space, they're absorbed and re-emitted by the water vapor. So we can use this fact to figure out what the temperature of the Earth is, because the temperature of the Earth is actually determined by the temperature 5 kilometers up in altitude. That's where those infrared photons can escape the atmosphere because there's no longer very much water vapor up there. And in fact, if we go to Hawaii, this observatory right here, it's an infrared observatory. It's built on top of the tallest mountain in Hawaii to get above the water vapor so that infrared photons from distant astronomical objects can be received by the observatory. So this is not quite 5 kilometers up, but nearly so. And if we calculate what the temperature of a planet like Earth is in the absence of any atmosphere, what we would find is about 0 degrees Fahrenheit, right? So very cold. But clearly Earth isn't that cold, except maybe Rhode Island right now. So we have to correct for the fact that there's an atmosphere. And we use the fact that this atmosphere is essentially 5 kilometers thick, because again, that's where the water vapor is. And also use the fact that the atmosphere cools off by about 12 degrees Fahrenheit for every kilometer height you go up. If you were to climb up Mount San Jacinto here just to the east, you'd find that it's quite a bit colder than down here in Riverside. And the average, what we call the lapse rate, is about 12 degrees per kilometer. So if we take 12 degrees, multiply by 5, we get 60 degrees, and add that to 0, we get 60 degrees Fahrenheit, and that turns out to be the average temperature of the Earth to within about a degree or so. So we can understand this temperature of the Earth by thinking about the coupling of the electromagnetic radiation that Maxwell told us about to the water vapor. Now let's now look a little bit more closely at light. And let's do an experiment where we have light that is shining on two holes and passing through, and those waves will then form what we call an interference pattern. So the waves will emanate from the two holes, and in some places the crests will meet together and we'll get a particularly strong wave. And in other places, a crest will meet a trough from the other hole, and there'll be some cancellation. So the intensity of the light will show this kind of pattern. Now, if we actually do that experiment with light, with a very sensitive camera, we can see this interference pattern, these lines of brighter intensity and less intensity. But now if we turn down the intensity of light, what we'll see is that what appeared to be a nice wave-like pattern just appears now as a bunch of random dots. Those are the photons, the particles of light that are being transmitted at this very low intensity. And as the light is so faint now, we can see that it's actually composed of these individual particles of light. So we can see simultaneously that light has a wave-like property and a particle-like property. And really, what we associated with intense light, those bright bands, is just places where it's more likely to find a photon. And the darker regions is where it's less likely to find a photon. So is it a particle? Is it a wave? Is it both or neither? Richard Feynman liked to say it's like nothing you've ever seen before, because it's not something that we encounter in our everyday experience. We have to use some very sensitive detector of light. But it was actually Einstein who made the connection between the particle-like nature of light and the wave-like nature through this equation, E equals HF. It's not E equals mc squared. E equals HF, which is actually a more profound equation than E equals mc squared. E is the energy of those photons, and F is the frequency. So this is the relationship between the fact that the particles come in lumps, these photons, and waves have a frequency, and this constant is called Planck's constant. So actually, Maxwell's equations are a kind of Schrodinger equation for light. And if we just make the change of interpretation to say that the intensity is not a measure of the height of some wave, but rather the probability that the photon arrives or not, then we see that Maxwell's equations actually contain not only relativistic physics, but quantum physics, again, in the 19th century, before the 20th century. Now, that photon nature has been exploited to great effect with solar energy. And in fact, Science magazine declared this last year that solar energy, solar photovoltaics is the breakthrough of the year. And you can see the reason why over here. This is a plot of the installed capacity for energy versus time. And so this is 2025. And this line is solar energy. Solar energy now has greater capacity installed around the world than any other electrical power source. Now, capacity isn't quite the same as total power output because the sun isn't always shining at full intensity, but it shows from the steepness how rapidly solar is taking off. It is now the cheapest source of electricity in most places, and in the United States, it is by far the largest increase in new electricity is coming from solar energy. So a spectacular consequence of understanding the photon nature of light and also the quantum mechanical nature of semiconductor physics, the semiconductors that make up solar cells. Now, returning to the wave-like nature of light or electromagnetic radiation, some of you may have assembled a crystal radio set. This used to be more popular in the past. It's basically a way to listen to AM radio without having any batteries. You don't need any batteries because you're actually listening to the power, the energy of the radio waves themselves. And so this family's gathered around a crystal radio set. There's an antenna, there's a detector, which is made out of a diode, a semiconductor device, and then you can tune and listen without any power. And this was important during World War II. Resistance fighters would make these radio sets so they could receive instructions from the Allied forces. So we've been interested in the question of whether, instead of exploiting the particle-like nature of light, whether we could use the wave-like nature of light to create power, just like this crystal radio set gets power from radio waves. And we've been thinking about how we might be able to make a new type of diode using high-temperature superconductors to try to directly rectify optical visible light. This is probably a crazy idea, but it's something that's kind of fun to think about, and we've been exploring this theoretically, and some simple diodes based on high-temperature superconductors have been constructed. Now, I want to return to something I mentioned near the beginning of this talk, which was the fact that Lord Kelvin had anticipated quantum physics many century prior to when it was the role of topology was recognized. And it came in solid state physics through this type of device. This is called an integer quantum Hall effect device. It's a semiconductor. You can see these are wires that are connected to it. This is a very early one that was built, I think in von Klitzing's labs. He's the discoverer of this effect. So he put it in a magnetic field, and what he found is that the resistance of this device did not just change linearly with the magnetic field, but showed these steps, these very precise steps in resistance. And in fact, they're so precise that they're now used as an international standard for resistivity. And we can understand that through topology. In fact, I showed you that we have objects that have like 0 holes in them, like a sphere, 1 hole in them, like a donut. Then there are objects with 2 or 3 holes, like a pretzel. Each one of these plateaus can be associated with topology, a topological change like that. And it's this robustness of topology under continuous deformations that explains why there are these sharp plateaus in the resistance. So amazing application of this seemingly exotic mathematics of topology to a practical device. And now there's a lot of interest in whether this kind of topological protection can be used in quantum computers to get the quantum computers to resist the effects of noise. I've been working with a group of scientists looking for waves of topological origin at UCLA. This is some of our group. This is Troy Carter, who was the director of the lab until recently. He moved to Oak Ridge National Lab, where he's leading their efforts on fusion energy. And here is our project leader, Zoe Zhu, who is a young assistant professor at Boston College. This is Jeff Parker, who is made the major advance theoretically. And these are some of the staff that are helping us do this experiment. So we're using a device called the Large Plasma Device. And this gives you a kind of view of it. It's basically a big magnet And inside the magnet, we can have a highly ionized gas. And I'll show you a little movie of this. So you can see these flashes. Those flashes are the plasma, the highly ionized plasma that is being formed. And we can insert these probes into the plasma and look for the propagation of microwaves. And what we're looking for is a microwave that will travel in a helical motion around the edge of the plasma, much like the Kelvin wave traveled around the edge of the body of water. And so I'll show you a little preliminary result. This is a cross-section of that cylinder, and you can see this kind of spiral motion that we've detected in our experiments. And we're going to be going back in May for another 2 weeks of experiments, hopefully concluding this experiment. And these kinds of waves may lead to some advances in fusion power. So this is a view of a magnet that's being assembled in Massachusetts at Commonwealth Fusion Systems. It's using high-temperature superconductors to get a stronger magnetic field than it would be possible with ordinary magnets, and they're hoping to produce actual fusion energy in a few years. I think they're a little bit optimistic, but they're probably ahead of all the other efforts at this point in reaching towards producing fusion energy. Now, I'd like to mention one other scientist. Her name is Eunice Newton Foote. She also lived in the mid-19th century, and she grew up in New England and upstate New York. Newton, it was her maiden name. She was a distant relative of Isaac Newton. And she was overlooked for basically the whole time until about 10 years ago. She is a climate scientist lost to history. She was also an advocate for women's rights. So she participated in the Seneca Falls Women's Rights Convention. You can see her name here, Eunice Newton Foote. She was mentioned by Susan B. Anthony. And we don't know very much about her. Here's one of the very few photos we have of Eunice Foote. But she is the first person to realize that electromagnetic radiation, infrared radiation, is absorbed and emitted by gases, and in particular water vapor, like we just discussed, and also carbon dioxide. And this is her short paper where she says that, thirdly, the highest effect of the sun's rays I have found to be in carbonic acid gas. Carbonic acid gas, that's the old-fashioned name for carbon dioxide. And she considered the fact that these gases, water vapor and carbon dioxide, might affect planetary temperature. So she's the very first scientist to realize that the composition of our atmosphere has something to say about planetary climate. And it's an interesting fact that the quantum mechanics of the absorption of infrared radiation by carbon dioxide was only fully understood in 2024 by a group at Harvard who worked this out in this paper. So now we have an analytical understanding of why carbon dioxide has the behavior that Eunice Foote discovered. So the APS, American Physical Society, is working to endow an award for early career climate physicist named after Eunice Newton Foote, because we're inspired by her story and would like to use that to recognize new physicists who are working on climate physics. So speaking of climate physics, I want to tell you about another project that I've been involved with, which is to try to remove carbon dioxide from the atmosphere. This is an incredibly hard problem. It's much easier to stop it at the source to reduce emissions by, say, using solar energy instead of burning coal. But we are drawing inspiration from the Earth. This is a picture of a mountain in far northern California called Marble Mountain. And you're seeing some snow melting in the summertime, and it's running off in these rivulets. And the rivulets have etched into this marble. It's really limestone. There's been a chemical reaction that has happened, and the carbonic acid in this snow that came from carbon dioxide in the atmosphere dissolving in water has reacted with the limestone and is being drawn out of the atmosphere. So we've been doing an experiment at the University of Rhode Island, which is Rhode Island's agriculture school. We've been spreading limestone on fields. Well, that's nothing new. Farmers have been doing that for a long time to adjust the pH of the soil. But what we've been doing is leaving it on the surface of the soil and measuring the change in the brightness of the soil. This device is called an albedometer. It measures how much light is reflected from the soil. And we think that by putting lighter colored rock like limestone on soil, we can reflect some of the sun's rays, causing an immediate cooling effect, while at the same time absorbing carbon dioxide and cooling the earth in the long term. And this is actually a satellite view of our field, and you can see that the treated half of the field is lighter now than the untreated control part of the field. So these experiments are just beginning, and in order to actually make a dent on Earth's climate, this would have to be widely adapted. Basically, farmers everywhere would have to be adopting this. So it's a heavy lift, but farmers have their own reasons for wanting to spread crushed rock on soil to try to improve its fertility. So maybe there'll be a meeting that where we can get a win-win situation, improving agriculture and removing carbon dioxide from the atmosphere and cooling the earth at the same time. So I want to end this talk by talking about some more exotic forms of waves. This is an observatory in Antarctica called IceCube. And what they're observing are neutrinos from distant astrophysical sources. And so what they've done is drilled holes into the ice and lowered down sensitive detectors of light that will pick up flashes of light when a neutrino interacts with the ice, which happens very rarely. Most of the time, the neutrinos just pass on through, but occasionally they'll interact and give a flash of light. And let's see, here's a view of one of the detectors being lowered down into the ice there. So it was realized not too long ago that neutrinos oscillate also. Neutrinos come in 3 different types, and there's electron neutrinos, tau neutrinos, and muon neutrinos, and they transform into one another as they travel through space. And in fact, this was the solution of a long-standing problem where it was observed that the number of neutrinos coming from the sun was about 1/3 what it should have been, based on the nuclear physics, the nuclear fusion going on inside the sun. Well, that was because these electron neutrinos were mixing into these other 2 types of neutrinos, and only the electron neutrinos were being detected. So that's another interesting oscillation that's being used here, in this case, to learn something about the distant universe. Another oscillation is maybe suggested by the spiral arms of galaxies. So how do galaxies form these beautiful spiral arms, and how do they maintain them? There's a theory based on a propagating density wave going around the spiral galaxy to explain these spiral arms. That's not the whole story, but that's a part of the story. And so there's wave physics at this fantastic scale going on. Then there are gravitational waves. So gravitational waves are waves in the space-time itself, distorting the distance between objects. And this is a cartoon visualization of the technique that's used at LIGO to detect the very slight oscillation in distance between these mirrors, using the wave-like property of light, laser light in this case, bouncing off of the mirrors and then coming back and interfering with itself from these 2 different arms of this interferometer. And as the mirrors oscillate, then that changes the brightness of the light that is received at the detector. Now, I want to emphasize how greatly exaggerated this is. The oscillation of these mirrors here is something like 1/4 of the diameter of a proton over a 4-kilometer distance. And it's just an amazing feat that Professor Barish and his team have accomplished in being able to detect such an incredibly small distortion of space-time. This is a simulation of the coalescence of two black holes coming together and emitting gravitational radiation. As they come together, the gravitational radiation is removing energy from the system, so it's drawing the two black holes closer and closer together, and the colors represent the space-time, and we'll see in a moment as those black holes get closer and closer together that waves start to emanate out from this, and a prediction that comes from Einstein's theory of general relativity. And they're going to slow it down the simulation right about now. And then we're seeing now these waves going out where they could be detected by the LIGO detectors. So a very different kind of wave. So there's so many different waves in the universe and all these different media, including space-time itself. Now, I mentioned that cosmic background radiation that decoupled from the atoms once the atoms became neutral seeded some initial density fluctuations in the universe. And this Sloan Digital Sky Survey looked at distant galaxies in 3 dimensions. And you can see that it's not just random, the galaxy is not just positioned randomly, but there's definitely some structure in these large-scale objects. So this is an example now of wave physics at the very largest kinds of scales that we can see in the universe. So CC is developing new tools to better understand these kinds of astrophysical and cosmological problems. And I'm really looking forward to seeing the advances that come out of the labs here. And I think that we can expect, as an offshoot from those advances, working on these seemingly unearthly problems, that there'll be some technological ramifications. And we've seen already in my talk, I hope I've made the case, that technology often follows from a deep understanding of physics. So what new kinds of waves are waiting for us to discover? Thank you.
Okay, we have time for a few questions. If anyone has a question, please line up here in front of either microphone, the front of the room.
Hello. This on? Yeah. Okay. So you said that during questions, someone might give you the opportunity to talk about waves and the weather. I'm here to give you that opportunity.
Okay.
So knock yourself out.
All right. Well, so one interesting fact is that the Rocky Mountains, or basically the mountains in the West, tend to set up a standing wave. And that standing wave often has the annoying property that there is a jet stream going up the coast, the east coast of North America. And that tends to steer these storms right up the coast. And they're traveling over
warmer water from the Gulf Stream, where they can pick up a lot of moisture. So it's this kind of combination of effects that leads to a northeaster. And so it's a type of Rossby wave that we talked about, these long waves deflected, in this case, by the Rocky Mountains and having this large-scale effect. Now, there's this idea that if the North Atlantic current, the Gulf Stream, the warm waters that are transported into the Atlantic north towards Europe were to stop for some reason, and there are some indications that maybe they're slowing down due to climate change, although that's controversial, then Europe might get a lot colder. And in fact, that was the subject of a movie, a rather overdramatic movie about climate change a decade ago. I think that was called The Day After Tomorrow. Actually, if you do an experiment with a climate model and you remove the Rocky Mountains, then that removes this kind of stationary wave. And that actually, some scientists have argued that that has a bigger effect on Europe's cooling effect on Europe more than shutting down the North Atlantic current. So that's an example of some wave physics that has some immediate application to our daily weather patterns.
Thank you so much for sharing your own perspective on such important and essential phenomena as waves. And I would like to ask you one question. Why did you miss, have you done it for purpose or not? Why did you miss anything about wave functions? About wave functions in quantum physics?
Wave functions. I like wave functions in quantum mechanics, and I work with them all the time, but I didn't want to go into those sort of mathematical details. So that's, but you know, the Maxwell equations are effectively a wave function equation. And when we square electric field, which we learn in electromagnetic theory gives us an intensity or a power, that what we're really doing is computing the square of a wave function, which is a probability. So yeah, that's the connection.
Hello, thank you again for coming to talk. It was a very, very interesting lecture. One thing I was wondering is, I remember in 2017, I believe it was 2017, when the LIGO team published their results. That was like a groundbreaking thing because we'd theorized gravity waves existed, but we hadn't actually proved it yet. And that was like, oh, they really do exist. Are there other types of waves that we think might exist that the theory says should exist, but that we're trying now to prove? Or is that like we don't know them yet?
Yeah, so those plasma waves, we made a theoretical prediction for these waves, and now we're trying to look for them. And those waves had not been predicted before, but by using the mathematics of topology, we have this prediction. So that's what inspired us to do this experiment, because anytime you make a prediction like that, you need to verify it by experimental means. So a question you could ask is, why is a theorist like me doing an experiment? Which I found incredibly challenging. And the reason is that plasma physicists, like condensed matter physicists, had not been going to each other's seminars. So they hadn't heard about these advances in topological wave physics. So it was just easy, instead of us convincing them, it was easier for us to just start working on the experiment. Although I should say that Zoe Zhu, when she was an undergraduate at UCLA, worked in that lab. So we had a leg up on the experiments, and there's a very talented staff, PhD level staff, that's really operating the machine. So it's this collaboration. Yeah.
Thank you.
Thank you for your lecture. I was just kind of wondering what the relationship would be between topology and the quantization of waves for, like, say, electrons or things like that, and how quantization can result from maybe the topological nature of these quantum objects.
Yeah, good question. So in the case of the quantum Hall effect, that resistance is quantized. And that really represents the fact that electrons come in lumps. And the wave function is, it has the interpretation of a probability. So we need to, the probability is either 0 or 1, whether there's an electron or not. We don't have that kind of quantization in the case of classical waves like the Kelvin waves or the plasma waves, or at least we're looking at very large scale waves that are, you can think of as containing billions of quanta, if you like. So we don't see that graininess. But in the world, the microscopic world of electrons, where we're sensitive to individual electrons, then we see this graininess. So the quantum of quantum mechanics is distinct mathematically from the quantization of the topology, the fact that the donut has one hole and the sphere has 0. There's kind of two different types of quantization occurring there. And that topological quantization applies to these classical waves as well as to the quantum waves. But the quantum quantization only is observable for these quantum waves, like in the integer quantum Hall effect. Yeah.
Great. Thank you very much.
Hi, thank you for your lecture. You mentioned something about Hendrik-Lorentz contractions. Could you touch back on that? Because I was a little confused by that part.
Okay. Yeah. So Lorentz was very talented mathematically, and he just noticed those Maxwell's equations that if he tried to apply the standard Galilean transformations, which say, for example, that if you're in a car moving at 50 miles an hour and you throw a baseball forward that, say, at 50 miles an hour, then that baseball is moving 100 miles an hour with respect to the ground. If he tries to apply that to the Maxwell equations, it doesn't work. And so that was a big surprise, I think, because you would expect the theory that, or the physics that Galileo and Newton worked, why doesn't it apply to these Maxwell equations? So he found that mathematically what you had to do in order to respect those equations, and then you had to start doing funny things like changing the length of objects that are moving. But he lacked a sort of philosophical principle that Einstein had, that the speed of light is the same in all frames, which clearly violates this idea that, if you're moving and you shine a beam of light, that light is still moving at the speed of light from both the point of view of the ground and with respect to the car. So, but he didn't really understand that that kind of conceptual background or framework that Einstein was able to capture. And then because Einstein was able to capture it, Einstein was able to understand more deeply the unification between magnetic fields and electric fields, and also E equals mc squared, and all these other manifestations, time slowing down, and so on. Yeah.
Thank you, because I originally thought you meant objects were oscillating in mass, and I was so confused when I heard.
Oh, no.
Thank you so much.
Sure.
Okay, if there are no more questions, one more.
Professor, thank you for making the trip out here. Really enjoyed the talk. My question is actually less related to the talk itself and more to your new role as president of APS. I'm curious as to how you see the future of APS evolving now with the onset of generative artificial intelligence technology, as our field continues to contribute to the development of this technology, as well as it begins to impact our own field, both in education and in kind of early phases of starting to contribute to our field. What do you see the role of APS being as we move into this future with this technology?
Right. I think this technology has many ramifications that need to be thought about. The APS has convened some workshops to discuss different aspects, the education aspect, and also how it can contribute to science. We're also concerned about ethical implications for our journals, for example, and energy consumption. The fact that these huge data centers that are being built require a lot of electricity. There are physicists who are thinking about new ways of computing for AI that are much more efficient than using graphical processing units. So using analog electronics, memristors, things like that. So those are just some of this multifaceted aspects of AI. And there are new there's a new division of APS that's concerned with AI, machine learning. So we're thinking about it in lots of different ways, and I imagine we might make some recommendations along the lines of policy, but we aren't ready to do that quite yet. Thanks. Okay. Right. Well, we don't have really definite ideas about this yet. There is some hint that in tokamak fusion reactors that are being built, that there may be waves of topological origin. We are using, for our experiment, a very simple geometry, this cylinder, because that makes analysis of the experiments much simpler than in these curved objects, these kind of donate-shaped fusion reactors. So one thing that I didn't really emphasize very much is this notion of topological protection, that these waves have a kind of robustness that ordinary waves don't. They tend to go around obstacles instead of being stopped by them. So it's possible that this kind of physics could be used to, for instance, heat the interior of a plasma, where it's hard sometimes to probe into the interior of a hot plasma. In fact, even in our experiment at UCLA, when we were first getting it going, we melted a bunch of the antennas that we were using to just try to make measurements, because the plasma is very hot, and at UCLA it's quite cold compared to the sorts of conditions that are in a reactor that's being designed to produce power. So that's, we haven't pushed that very far yet, because we're trying to still understand the basic physics. But we see over and over again that understanding the basic physics is often the pathway, the entry point into making some technological advance. Mm-hmm.
Thank you for a wonderful lecture. Really spectacular. You showed a chart of all the different waves. I call them species of waves. But do all these waves interact linearly? Do you just kind of pile them on each other and add them up and get it? Or are there emergent nonlinear properties? And if so, might they be things that we've never seen before, because we've never seen waves that way?
Yes, thank you. So often the waves are pretty linear, but not always. So a famous example was the discovery of a soliton. So it was observed that in some water flow in a channel, a canal actually, that you could have this lump of water that would be moving down the canal without distorting in shape. And so this is a nonlinear phenomena. Nonlinear phenomena is much harder to understand usually than linear phenomena. And that's actually a particular unsolved challenge with this topological wave physics. It's all been developed in a linear framework, and we're just starting to think about how to adapt it for nonlinear systems. For those water waves, for example, if the amplitude gets too high, they break.
waves breaking on a beach. That's a very nonlinear process and can lead to turbulence. So how to combine this topological physics with, say, turbulence is an unsolved problem. I have a PhD student working on that right now, but I think it's going to be a long time before we have a clear understanding of how to combine these two things together.
Thank you for your lecture. What I was kind of curious on were the neutrinos, because you expanded on how they changed phases. Was that phase change via oscillations similar to waves?
Sure, it's a type of oscillation. So it's it's described by effectively a wave-like equation. And technically, it has to do with the fact that the mass eigenstates of neutrinos is different from their flavor eigenstates. But it's not very complicated physics, but it's a nice example of wave physics in a completely different context. Yeah.
Are there any topological implications for that, or not as of yet?
I don't know. Maybe a particle physicist might be able to answer that question. Yeah, good question.
All right. Thank you all for coming, and let's thank Professor Marston once again.